Alright, so today we'll learn about the equations of motion. So this is our lecture 3. First topic we are going to learn about is are the equations of motion. So, the equations of motion, which we are going to derive for the curriculum of IIT JEE, constrains us to not go beyond constant acceleration. So we'll assume the highest amount of highest amount of gradient any motion can have is till the point there is constant acceleration. Okay, so first let us define what each quantity is. So the first quantity is displacement, right? So displacement is the shortest distance between 2 points A and B. Distance is it's not going to be the shortest distance, but it takes on any kind of a trajectory, and then basically if you do the closed integral of that path, that will give you the distance. Displacement is a subset of distance, meaning one of those distances between A and B will be also the displacement. The displacement is a vectorial quantity. It will have a vector. So the displacement in between point A and B is displacement of point B with respect to A is displacement of point B with respect to the position vector of point B with respect to ground minus the position vector of point A with respect to ground, and thereby you can find out what the displacement will be. So anywho, let's get back to the equations of motion. So the first law which we are going to derive is based on the fact that um, if let's say there are 2 points A and B, okay, and a person starts to move, uh, and let's say this point A is attached to that person, and somebody is watching him in the ground frame of reference, and let's say that the vector DAB with respect to dt is decreasing at a certain velocity v. Now suppose that this velocity v is also changing with time. So if this velocity v, the rate at which the 2 points A and B are coming closer to one another, is also changing in time, then we'll write that change in time as acceleration, and we are only interested in the magnitude for now, and then we can add the directionality and things like that. So you can also write it in terms of dv vector with respect to a vector, and so that way vectorially, if the acceleration is working against that velocity, then we will also take care of it, or if it is working in the direction of velocity, we can also take care of it. So as we were discussing it yesterday, whether it's I cap or minus I cap, everything comes together when we think about this problem in vectorial terms. Okay, so let's say this acceleration is a constant value. Then when you integrate this dv with respect to this constant acceleration from time 0 to time t, and velocity when you integrate from initial velocity u to final velocity v vector, you get v vector minus u vector equal to a vector times t. You get v vector to u vector plus a vector times t. So this is my first equation of motion, which is based on the fact that the velocity, the rate of change of velocity is a constant given by acceleration, and then when you integrate both sides from time 0 to time t and from initial velocity u to final velocity v vector, you get the first equation of motion. Now coming to the second equation of motion. Okay, so I'll give you guys a couple of minutes to catch up what's written on the board, and then we'll move forward. Okay, so again, just keep in mind what we are trying, what this equation is based off. This equation is based off the fact that the rate of change of velocity is a constant given by acceleration, and when that constant acceleration is provided, you can always integrate this equation on both sides to get this vectorial equation v vector equal to u vector plus a vector times t, where the acceleration is constant. This u vector is the velocity at the initial velocity, and this v vector is the final velocity. All right. Okay, so now let's go to the second equation of motion over here. Okay, so the second equation of motion is based on the first equation of motion, and so the first equation of motion stated that dv vector by dt is equal to a constant vector called acceleration. Now this v vector by itself is also the rate of change of displacement, as we were discussing in the last equation of motion, that the rate of change at which point A is approaching towards point B is that velocity vector. But if you write those terms vectorially, you don't have to worry about the signs, and you can simply write dy dt of dy s vector with respect to the displacement vector with respect to time is this a vector. Okay, and these displacements could be also infinitesimal displacements, and this notion can also hold for distance, but we'll come to that later. So basically what it boils down to is d square s vector with respect to dt square is a vector t. Okay, so when you integrate it first, you get ds vector by dt equals a vector times t plus another constant vector 1 c1, and then when you integrate it back again, then you get a vector t square by 2 plus c1 vector t plus c2 vector. Okay, so there are two integrations which we are doing here, and basically the notion is very simple. If you have dy by dx, d square y by dx square given by a constant number, let's say a, then what you will do is, first off, you will write this equation as d by dx of dy by dx equal to that constant number. Then you will get to integrate both sides, and let's say this number is still constant from x1 to x2, from dy dx at that x1 value, dy by dx at that x2 value. So you'll get dy by dx, or either you can do it like this, or you just do the definite integration. Sorry, I should have done the definite integration. So when you do the definite integration, you get dy by dx equal to ax plus b. Okay, so this is the way of doing the definite integration, and then you get again dy dx of y equal to ax plus b, and then what you do is d of y equal to ax dx plus b dx, integrate it, and you will get y equal to ax square divided by 2 plus bx plus c. Okay, so this is how you'll get it based on constant acceleration value, right? we'll go into the trajectories and all those things later. But this is the way which we are following here as well. Instead of having the variable x, we are having the variable t, and and instead of having a scalar equation where a, b, and c are scalars, we are having a vector, c1 vector, and c2 vector. And similarly, instead of having a scalar valued y, we are having a vector valued as which is also a vector. Okay, so now at t equal to 0, we know that the initial velocity was u. So we'll catch this equation, okay, which is also the equation for velocity when we integrated it one time, and we throw in t equal to 0. So my v vector at time t equal to 0 is c1 vector. If you throw, so let's write this as equation 1. After first integration with respect to dt, with respect to time, you get the second equation, and after this one with respect to time, you get the third equation. So at time t equal to 0, you get ds vector by dt. Oh, sorry. At time t equal to 0, that initial velocity was u vector equal to c1 vector. So my c1 vector is nothing but the initial velocity of the field. So we'll write this as s vector equal to a vector times t square by 2 plus c1 vector plus u vector, which is the initial velocity over here, times t plus c2, okay, plus c2 vector. Now, if at time t equal to 0, my location is also my radius vector with respect to origin is also 0 vector, then this c2 vector will be 0 by simply putting at time t equal to 0. Let's assume that my s vector was 0, meaning I'm starting from the origin. So s vector, if you put t equal to 0 here, so on your left you also have 0 vector equal to, so if you put t equal to 0, this term is 0, that term is 0 plus c2. So your c2 vector will become 0. So your s vector will become u vector t plus half a vector t square. Okay. So this is our second equation of motion under the assumptions. Always remember the assumptions before using them in your exams. Just don't blindly write your equations without thinking about the assumptions. So in the second equation of motion, you have to always remember that we are talking about a constant a vector. Okay, your acceleration is constant, the magnitude of that acceleration is constant. It can be also the vectorial, where magnitude is same, but the vectorially the acceleration is not constant, and we'll go into all those. But over here, at least think about linear acceleration, and that magnitude of acceleration is constant, and that the direction continues to remain the same in linear terms at least. So the acceleration is constant, and also the fact that we are assuming the initial velocity to be u, and we are assuming the initial position or the radius vector to be 0 vector. Okay, so with that, that concludes um, our second equation of motion in here, and this over here is the reference which you need to go through in order to derive this second equation of motion. And it is very important again to look into the fact what are the assumptions behind a certain equation of motion. Okay, so thank you, and again I would say I'm going to give you guys a couple more minutes so that you guys can have your notes ready and can take the key points from this screen at least, and then we'll go to our third and final equation of motion, again assuming a constant acceleration vector, but then in the first equation of motion and second equation of motion, time was a variable we were concerned about, and you will see that the first equation of motion we wrote again. So this is again going back to the first equation of motion, which was v vector equal to u vector plus a vector times t, where my assumption was that this acceleration is constant and this is my initial velocity. So all over here are assumptions in order to get my final velocity. And the second one, which we got over here, is s vector equals u vector times t plus half a vector times t square. Again, we can see that both the first equation of motion and the second equation of motion has the initial velocity, acceleration, and time involved in order to get the final velocity and the final position. But on this one, my u vector is again initial velocity. This acceleration vector is a constant acceleration vector, both in magnitude and direction. We'll come to very interesting cases later on. What happens when a magnitude of the acceleration remains constant, but the directionality changes, or um, the direction remains constant and the acceleration changes. The direction remaining constant and acceleration changing, that is not going to be covered, and it's outside of the scope of IIT JEE, and mostly it is also not required. Even if you start doing some numerical techniques further in your careers, it will not be required to go beyond acceleration. But the physical term for changing acceleration as a function of time is called jerk, and that is given by dA vector with respect to dt. And that happens when there is a bump on the road and you suddenly decelerate and then again accelerate on the other side of the bump. You get a jerk due to changing acceleration. So again, we'll not go into all that, but yeah, it's good to know things, and that's what I'm telling you over here. Take a couple of minutes, try to grasp the concept once more, and get your things which you need maybe for your further referencing from this screen. So now we'll go to the third equation of motion. I hope um, this is all clear. Again, if something is not clear to you, please use the comment section and write to me. I have already provided my email address in the second lecture's description section, but again it's jee.answerman@gmail.com. So the story behind Answer Man is very interesting because of the fact that there are superheroes, Spider-Man, Superman. In India there was a superhero called Shaktiman, but now there is Answer Man. Hopefully I can answer some of your questions, if not every one of them in physics. Alright, let's go to third equation of motion. Alright, for the third equation of motion, again, as I said earlier, the first equation of motion looks like this, the second equation of motion looks like that. Both of them have the three variables, again and again, the initial velocity u vector, the constant acceleration a vector, and the time variable. But now what we are going to change all of that, and we'll look into it how. So basically what we are going to do over here is very simple. We are going to use equation 1 uh, and equation 2 together in order to derive our third and final equation of motion without having to have the time variable any further in the equations of motion. So we are going to write our time variable as uh, and it's going to be tough because it's written in terms of vectorial quantities. So I'm going to ease it and make sure that we have taken into account all the directionality, um, and with directions taken into account, I'm going to write this equation in its a scalar format as v minus u by a. So let's say if you have initial velocity in the positive x direction, your final velocity happens to be in the positive x direction or 0, and your acceleration is going to be in the positive x direction, then your first equation of motion will look like v equal to u plus at, because everything has I cap in common. Um, and then you can simply take v minus u over a. In the other case, if your acceleration is negative in the minus I cap direction, then it will become v equals u minus at, and then your time will become u minus v divided by a. So basically, there will be retardation involved. In one case, in the acceleration case, the final velocity will be greater than the initial velocity. In the retardation case, your initial velocity will be greater than the final velocity. And those will be the two variations. There could be also variations in terms of the initial velocity in the opposite direction. So for example, you are throwing a ball upward, and then you would like to know the final velocity when the ball hits the ground, right? So your u vector is in the positive j cap direction, but your final velocity is in the negative j cap direction, as well as your gravity, which is in the negative j cap direction. So for this case, for example, you'll have, so v will be written as minus v because it's in the negative j cap direction. U will be written as u j cap, and this acceleration is minus g, and it's minus g because it's in the minus j cap direction, and you will write it like this, and then you can figure out the time from there. Or if the time is given, you can figure out the velocity from there. So that's that. So if we write the, let's say we have taken all the signs there, and we are looking at with all the signs and everything put together, you can write your time as v minus u divided by a. Okay. Um, and then the other way, you can also probably write it in another way. I did not want to go into that, but I guess we can get into that as well. You can write, you can possibly write this time thing. Um, well, I would say let's forget it for now. So just worry about the scalar part of the equation, and assume that you have taken care of the signs as per needed in the problem. Then once you get that time, if you put it in the scalar valued second equation, or the scalar analog of the second equation, then this will look like su. Instead of time, you will put this variable in, you will put this substitution in there, in here, or in here for this and this, you know, first and second power of that same variable in there. So this will be half v minus u divided by a whole squared. So this will come out to be uv minus u squared divided by a plus half times a, because a will cancel the a square in the denominator, v squared plus u squared minus 2uv. Okay. So if you take this denominator and multiply on the LHS on both LHS and RHS on both sides, you get uv minus u squared plus half v squared plus u squared minus 2uv. You would get Um, so this, so v squared divided by 2 plus u squared divided by 2 minus uv and uv will cancel each other. This u square, so v squared by 2 minus u square 1 minus half. So this will come out to be v square minus u square by 2, and it will literally come out to be v square minus u square equal to 2as. Alright, so this will be my third equation of motion. Of course, I have provided the scalar analog of this equation, okay, uh, and and a vectorial analog of this equation could be also provided. But for now, I think this is good enough that we have provided vectorial analog, a scalar analog of this equation, and from here, the three equations of motion which you need to know for this problem uh, can be arrived at. So, for example, if you're throwing a ball toward, you're throwing a ball upwards and then would like to know the velocity v, and you know from which height you are throwing the ball up, let's say that height is h, you don't have to now first figure out how much time it took in order to get uh, your your final velocity. What you can do is this v will be negative of v squared. So this is also a sign, minus u is in the positive direction, so u will remain as u square equals 2. The g, or uh, the acceleration is downwards, that will be negative g. The displacement, not the distance, but the displacement will be minus h, because that much of displacement it will cover in the negative x direction. So basically you can get v square equals u square plus 2gh. So if you know the initial velocity, generally the constant of gravity, this um, value of the gravitational acceleration is known to be 9.8 meters per second square. People sometimes take it to be 10. So this is a constant number, and based on the height, the velocity is proportional to uh, to your height power half, and velocity is proportional to your initial velocity. Okay, so these are some of the common questions. Sometimes you will be asked to solve these type of problems, or provide different different flavors of these type of proportional relationships as far as responses in IIT examinations are concerned. So with that, I would like to say that we have covered all three equations of motion. First two in the vectorial format, and the third equation in the scalar format, where we are writing v minus u square equals to as. And this is assuming the fact that your acceleration is a constant number, v is the final velocity, u is the initial velocity, and s is the amount of displacement covered in between your initial position where your velocity was u, and your final position where your velocity became v. So with that, I would like to again say thank you for taking the time and go through my lecture, or go through what I'm trying to do here. So I would like to give you guys again a couple of minutes so that you can capture what is there on the screen. If you have any further questions on third equations, on the third equation of motion, please do not forget to to write your questions in the comment sections, and I'll try to get back to you as soon as I can, if I could. Thank you. So, in the second part of the lecture, I'll try to quickly do a couple of examples using first, second, and third laws of motion, right? We'll try to basically stick to the third law of motion if we don't have to figure out the amount of time it required in between the final and initial events as far as motions are concerned. But yeah, if there is a requirement to figure out how much time it required and things like that, then we'll possibly hit on the first and second law, first and second equation of motion. All right, so we'll start with a really simple example. Let's say there is a person who is on top of a building, and for the fun of it, the building's height is 9.8 meter. Okay, and he throws a ball in the up direction. Okay, at a certain velocity u, and when this ball hits the ground, it hit the ground at 19.6 meters per second. Okay, so we'll now try and figure out what is that initial velocity u and how much time did it really take to go from this instant where he threw the ball up to hitting the ground. Okay, so let's do this equation. We can certainly start since time is asked for. How much is the time? So we'll certainly use the first equation of motion. Think about the first equation of motion. It was vectorially written as v vector equals u vector plus a vector times t. The final velocity is minus 19.6 j cap. The initial velocity is not known. The acceleration due to gravity is g vector, which is minus 9.8 j cap in SI units of meters per second squared. We don't have to go to that. So this is minus 9.8 j cap, and we are interested in the time as well. So in order to arrive at that, so we should start with something which has all the information herein covered, and there is only one variable to be figured out. So for doing that, we have to go to the third equation of motion, where we have the final velocity minus the square of final velocity negative square of initial velocity is equal to 2as, where both a vector and s vector have their respective directionality provided therein. So we'll write the final velocity as minus 19.6 again. This is not vectorial, but we make the notion of it as vectorial. So this is minus 19.6 u squared, minus 19.6 squared because it's in the negative j direction. U, or the initial velocity, is in the upward direction, so we write this as u, not making it minus u of minus u and then squaring it. I'm just squaring it as it is, equals 2 times the g vector is downwards, minus 9.8 times s is also minus 9.8 as the displacement traveled by the ball. The distance will be much higher, but the displacement is only minus 9.8. Okay, so my u square will turn out to be 19.6 square minus 2 times 9.8 squared, okay, which would turn out to be 2 times 9.8 squared, which will be 9.8 square root of 2. meters per second. So if we throw the ball upwards with a velocity of 9.8 square root 2 meters per second, it's going to suddenly hit the ground at a velocity of 19.6 meters per second. Again, there is no drag associated in this equation of motion. This is assuming that your acceleration or the notion of gravitational acceleration remains constant, although it changes with respect to height, and we'll go and learn about that on our chapter in gravitation, but I'm not going into that in this particular lecture. And assuming that your constant for gravitational acceleration remains constant at 9.8 meters per second square. With that in mind, applying the third equation of motion, where our variables of interest were the square of final velocity, the square of initial velocity, the acceleration due to gravity, and s, the displacement covered, we find that our initial velocity is 9.8 square root 2 meters per second. And that also in the positive j cap direction, because we are throwing the ball up initially. And if we supply this equation to the first equation of motion, what do we get? We get minus 19.6 j cap is equal to 9.8 root 2 positive j cap minus 9.8 j cap times t. You can take out the j cap because everything looks to be in the j cap direction only with their signs. Now will remain on the board. So this is minus 19.6, 9.8 root 2 minus 9.8 t. So 9.8 t will become 19.6 plus 9.8 root 2. So your time will become 2 plus square root of 2, because when you divide 9.8 with respect to 19.6 and 9.8 to square root 2, you get 2 plus square root of 2. You can also do the calculation and figure that out. So I'm guessing your time will be around 3.41 seconds from its initiation in the upward direction towards hitting the ground at 19.6 meters per second. So with that, we covered how much time it will take for us to throw the ball up and hit the ball on the ground. That will be upwards of 3 seconds, even more, around 3.41 seconds. And then we also figured out how much should be the initial velocity with which we should throw the ball up in absence of any drag or any other type of decelerating factors or accelerating factors for that matter, that the ball hit the ground with 19.6 meters per second of final velocity, and that velocity comes out to be 9.8 square root 2 meters per second. Okay, so we'll do another example where instead of throwing the ball up, we'll throw the ball down and see how that changes the answer. And with these two examples, we'll say that we are good, and I'll leave it to you guys to ask me further questions in the comment section so that I can take care of your other aspects of motion which you may be worried about based on these equations of motion. Again, I'm going to give you a couple of minutes over here so that you can take notes as required by you, and then we'll move to problem number 2 to be tackled shortly. Thank you. Alright, so I believe that you have been able to take appropriate notes from what I was trying to do over here. So we'll move to our second example. in the second example, instead of throwing the ball up, we'll throw the ball down at a velocity of u. It will still hit the ground with a velocity of 19.6 meters per second. And we are interested in what this initial velocity is, was, is, and with the building height being 19.6 meters, the acceleration due to gravity negative of 9.8 minus 9.8 meters per second square in the minus y direction. And so the tasks are same. We just want to figure out if the quantities which we determined in the last example still remain true over here. One quick observation which I would like to throw in is that when I throw the ball up at a certain height, when I'm throwing the ball up, when it comes to the same level, it will have the same velocity. So if I'm throwing something up with a certain velocity u, when it comes back at that certain height, so remember in the last example we were throwing the ball up at a certain velocity u, and then when it skyrockets and comes back, then it will have the same velocity u by symmetry when it reaches the same level. But that's just due to observation. We are hoping to see that the initial velocity will remain the same, but the time for going this distance of or having this displacement of 19.6 meter will be much shorter. So we'll validate whether this observation still holds true or not, and we'll go through the mechanics of it and figure out for ourselves if that is still true. Okay, so let's do that really quick. So again, we are going to throw in our first equation of motion, which is a vectorial equation of motion written as v vector equals u vector plus a vector times t, the final velocity being 19.6, negative 19.6 j cap. We don't know about the initial velocity u vector. We know that it's going to be j cap, but we don't know for sure how much the magnitude is. We kind of know from the observation I just talked about, but then again, it's very difficult until and unless we do the math and prove it for ourselves that it is still indeed the case that if the ball would have been thrown up at a velocity of u, the same velocity will be recovered when the ball is thrown down, just because of the skyrocketing symmetry. But let's not go into that. And this acceleration due to gravity is minus 9.8 j cap times t. So if we take out all the j caps, we are looking at minus 19.6 equals u minus 9.8 times the time required for it to reach the ground level and hit the bottom of and hit this level of the building, bottom level of the building. So this is that. We'll throw in the third equation of motion, which is written as v square equals u square plus 2as. This is negative 19.6 whole square. We don't know the initial velocity. We know that it is in the negative direction, negative j cap direction, so we'll write it as minus u whole squared plus 2as. We'll write g vector as minus 9.8. This is a scalar equation, so we assume like the positive direction is up, and then throw in the signs as we go in this equation. This is negative 9.8, and then this displacement is also going to be covered from initial to final position in the negative direction, negative j direction or negative y direction. So that's about that. I think the building height was 9.8 in the earlier case, so let's just make it 9.8. In example number 1, I'm just forgetting it. Just check for yourselves if that is still the case. Now we'll try to figure out what is my velocity u square. That is 19.6 whole squared minus 2 times, because these things will become positive, because when negative and negative multiply with one another, negative values multiply with one another, if there are even number of terms, then you'll have a positive number out there. So this being the case, we'll write this as 2 times 9.8 whole square is u square. So your u value will be 9.8 root 2 meters per second, which is the same which we expected and was the case earlier. So no matter how you throw it up or down, due to the skyrocketing symmetry, the velocity when it comes back, it will achieve the same velocity for the same height. Okay, so anywho, that's not the question here. So that is my initial velocity. Let's try to figure out what will be the time, amount of time with it. It's clearly in the earlier case, or in example number 1, my ball was thrown up, so it has to cover this distance, then come back this much distance, and then cover that distance. So that would have been much higher amount of time compared to over here, where these steps are not any longer required, and where distance also becomes the displacement of 9.8 meters. Right? So if we put this back in here, in the first equation of motion, we get negative 19.6, 9.8 root 2 minus 9.8 times t. That leaves us with 2 plus root 2 seconds again. I'm just wondering why. Oh, so over here it is minus uj cap, because we are throwing it down in the and direction. This will be minus 9.8. Sorry about that. So this will be 9.8 times t equals 19.6 minus 9.8 root 2. So I'm looking at 2 minus root 2 seconds, which is about, if you do the math, it will come out to be around 0.6 seconds to cover this distance of 9.8 meters, whereas in the earlier case, if you remember right, when we threw the ball up, the time required to do this maneuver of doing this entire, covering this extra distance of going up and coming down was 3.41 seconds, right? So with that, this concludes this example. One trivia is that, if we know the total amount of time when the ball was thrown up, it was 3.41 seconds from last example, and we know the amount of time if the ball has been thrown down, how much time it required to cover the same amount of distance. We can possibly tell the amount of time the ball was not traveling in the displacement direction, but was just skyrocketing above its level when it was thrown up in the previous example, and that will come out to be 3.41 minus 0.6 seconds, which will be around 2.8 seconds of upwards movement and downward movement till it hit that level of this terrace again, and then it started moving downwards. So with this example, I think we have some material in here for you guys to look into, and then ask any questions you may have as far as equations of motion are concerned. So with that, I'll leave whatever I have tried to do in here for you for another couple of minutes, and then we'll probably move to a next topic, or we'll probably move to a next lecture, probably today night or tomorrow morning, respectively. So I hope this might have helped you in a positive manner. And if not, if you find that my lecture style could be improved, just let me know and I'll try to do that. Um, we are all students here. We are trying to do our best in order to make it through. It's just that I'm on the other side of IIT compared to you guys. But again, your learning never stops. So it's better to ask as many questions as you can so that we can all be successful in our own pursuits. Me in distributing what I know, and you in telling me even more important problems which we can solve together. Thank you and have a great day. Bye.